Hello everybody, please confirm that you hear me. Okay, so hello in my next stream. Today there will be two things I will be solving or talking about. One thing is that I will show you some of problems from our recent competitions, like ACM qualifications in my university. And the next thing is that maybe you want to suggest some problem. It shouldn't be either very easy or very hard, just maybe something in the middle. So let's do that later. I must find a link to a contest. So in the meantime, does anybody here plan to participate today in the Codeforces round, maybe? There is, I think, a contest called Lift Challenge. And we'll start with problem E that you see here, Rika with XOR. Unfortunately, I don't know the initial source of a problem, so I can't give you a link, and this is like a private contest that was held in our university. But you will see how to what to do when it's impossible to submit a solution, because we can just write a brute force and compare our solution locally. So the problem is that we are given two integers, m and n. So this is the only thing in the input, both up to 1 million, also some test cases. And we are asked to find this product. So where the strange symbol in the middle means XOR. So for example, for m equal to, let's say, 2, we are asked about the product of n XOR 0, n XOR 1, n XOR 2. Just to make sure that we understand the problem correctly, let's implement the brute force solution, just anything that would work, but of course very slowly. So let's just brutally, naively implement this solution. And later we will see what I think useful technique we can use here to solve the whole problem. As I said in some of the previous streams, it's good to create functions for separate things, not to write the whole block of code in the main. So a test case is a perfect example of something that we can extract the separate function. So we are asked about, so we read n m, and answer is some product from 0 to m. We multiply answer by n XOR I, modulo some mod. And let's see if this works. Always save the input file, the sample input, to a file, just to not copy it again and again, to have it in one place, to then conveniently run it. And we see that the answer is correct for first two examples, but it's incorrect for the last one. So maybe the program is correct, but there is some overflow or something like that. Let's see. Maybe modulo is wrong. Yeah, I forgot 1 0 in modulo. And now it's correct. Well, when it's very easy to create a max test, of course we can do it. So here, to the sample test, let's add one more test, where, for example, both n and m are 500,000. So here we see that it takes a bit more time. Let's measure it. In Ubuntu you can measure it with time function. If you use Windows, you should find the equivalent function in your system to be able to conveniently check that. Also be aware that in Microsoft Visual Studio, when you run it with some button to open a new window and create a new instance of terminal, here Visual Studio will tell you how much time it took to run. The bad thing is that that value is often bigger than actual running time. There is some overhead from running this terminal, so it isn't a good way to measure the time. What is the effect of creating functions except the repeated usability? There is no effect about memory or runtime. It will not be faster. It just, one thing is that it will make your code look nicer, easier to read. The other thing is that because of that, you will make less bugs, or it will be easier for you later to find those bugs. And the third thing is that if you want to work in a company, you must learn how to do that. You must code like this. You can just put everything in main, because nobody writes like that in actual companies. So there is no advantage of putting everything in main. Just use functions. And to everybody watching, feel free to ask questions like this, because this is exactly why this stream exists. So there would be some interaction between us, and you can ask questions like this. And I think it's a very good opportunity for you to learn a lot of things that wouldn't otherwise be explained or written anywhere. So we see here that on one max test, not even max test, because it was 500 billion, and here the constraints are up to 1 billion, so it's too slow. Also, there are several test cases, up to 20, so it's too much. And we must do it faster, and we'll use some general technique. But instead of jumping into that, let's see what we can do and what should be a thought process. So, since XOR is something that works for bits, let's imagine n written in some binary form. Maybe let's make it a bit shorter. Okay, so first, when we multiply the answer, the product, by n XOR 0, we just multiply it by this value. Then let's make it even shorter. So this was XOR 0. Then XOR 1 we have something like this. Maybe let's put it this way. So what are the next and the next values that we multiply the answer by? Then yet another value is the same begin, and now we do XOR 2, so the second last bit changes comparing to the initial value. So this is just, we say that this is n from the input. And then for 3 we have something, and so on. So we will not write more values, but very important thing to notice, I will answer a question in a moment. Very important thing to notice is that the first, let's say, 4 values that we multiply are very similar to each other because only 2 last bits are changed. So it's visible here, and it makes sense because we do XOR by some value that only changes last 2 bits, and all the remaining bits are the same. And a similar thing, of course, will happen for the first 8 values, because by XORing by 0, 1, 2, and so on up to 7, we only change last 3 bits. Also, important thing is that the order of those numbers do not matter. So, what it means is that here it didn't matter what are the last 2 bits of n, because we iterate over all possibilities here. We have 1, 0, 1, 1, 0, 0, 0, 1. So the first 4 numbers, the product of them would be the same, also for n equal to just this number with 2 zeros at the end. Regarding the question, your 2 compilation commands which you have mentioned in first videos, please. I mentioned it a few times, that I have one command to run with debugger flags. I'm pasting it now in chat, and the other one that I use to check the running time of my program. So here, for example, to check later time, I used F8, that is in my IDE. It's binded to fast compilation, to compilation with O2 optimization. But what is more useful are those flags that you see in the first command, sanitizers, that allow me to catch more errors. When I do some mistake and later I run my program, sometimes they will warn me, or they will show me this is exactly where you have out of boundaries error or something like that. I do recommend. Possibly some of them will not work in Windows, so just check what compiles, what doesn't. Maybe, for example, this glib cxx debug will not work. Just leave here whatever works in your system. Okay, so our observation here should be in some way used in the solution. And we notice that for first some power of 2 numbers, only the last bits are changed. For example, in first 2 power 10 numbers, we try all possible last 10 bits. And for example, if m would be equal to, let's say, 2 power 10, so 1024, then when we read n, we can skip the last 10 bits, they don't matter, and we are just interested in the answer for the first 20 bits about the whole product. So here what we could do is do some pre-processing on our own machine. That is a general useful technique. Some people think that it isn't a very nice technique or you shouldn't use it, but it isn't forbidden, and if the statement says that there is some particular modulo, the modulo is given in the statement, so because sometimes you read modulo from the input, and this is usually when you can't do pre-processing. But if modulo is given, then you can, and it's perfectly fine to do that. And what we can do is find once on our own machine, compute the answer for some number, and for n equal to some number with last 10 bits equal to 0, and then to find the product of next 1024 numbers, and we can paste it in our code, and we can paste a big number of values there. Usually the limit for the size of code you submit is something around 100 kilobytes. That means what means 100,000 characters in your code. So usually there's something like source code size 100 kilobytes. And if we are allowed 100,000 characters, it means we can have in our code something like 10,000 numbers, each of size 10, like 10 digits long. So the idea is that here what we should do is, let's say for every number n, starting from 0 up to something, let's say that for a moment it will be up to 1 million. It will be in fact a bit longer, and let's in a moment think what we exactly should do. So let's say it's better to use some constants multiple times in your code, so let's just create a constant for this. Let's call it, so the number of bits at the end that don't matter, for example, let's call it k. Let it be 10. And let's see what happens. So if k would be 3, then we would want to find answer for just n equal to zeros, then answer for 1 and 3 zeros, then the same for 1 and 4 zeros here, something like this, and so on. So because we noticed the product of first 8 numbers, so 2 power k, will be the same no matter here the bits. So if we once compute this value, the product for this n, then we also know the answer for this n, and so on. So here what we do is we try every n with jumps 2 power k. So this is in C++ 2 to the power k. Here we find the product. We multiply product by what? N XOR I modulo fixed modulo, that's given in the statement here. And let's say that we just for a moment print product. And what here we would get is some number of pre-processed numbers that we later want to paste into our code. So here, for example, I would save it to a temporary file, let's say tmp, and then I can take this value and paste in my code. What is still a bad thing is that there are a lot of values, namely something like 1 million values. Why? Because here, if I try every 1000 n, then I get 1 million possible values of n. So, what I should do is I should change this jump, this value of jump. What will be a good value, for example, is, let's see later why, is 10 power 20, because then what I want to get is only 1000 preprocessed numbers that when I copy-paste into code, they will take like 1000 numbers times 10 characters, 10 digits. It will be 10,000 characters, so it will be fine. Okay, and we got some numbers. We want to paste them into code, what is hard in this format. So instead of that, let's put it with commas. So here I will write a comma, because then I can paste it as an array. So I have a long line with numbers. What I can do is create an array, let's call it preprocessed, or just pre. And like what I created is a very, very long line. And it's fine, it will compile correctly. And let's think how to use it to speed up our main solution. So here I will, for now, remove this slow part. Of course, the issue is we can't leave it in our code to just compute once and use it in test cases, because it's still a bit too slow. It could be too slow to solve our program if, for example, time limit is like 1 or 2 seconds and it takes 3 seconds to compute. But sometimes it's necessary to do pre-computations like this. And here, let's think. If m is equal to this, like 2 power k, then we know the answer. So we could write, if m is equal to this, answer is equal to what? Pre of something, and that something is n divided by 2 power k, because among our pre-computed values, this is the product for first 2 power k values, then this is for values between 2 power k and 2 times that, and so on. So like the next 1 million numbers. So when, for example, n is slightly bigger than 1 million, so it is among these values represented by this number, we know that for every n in this interval, so for what we claim is, if m is equal to 2 power k, then for every n in interval between, let's say that 2 power k, we can print like this just to make it easier to read, between 2 power k, so I times 2 power k and I plus 1 times 2 power k, the answer is pre of I. This is what we know. because we noticed here that no matter the last bits, so the value of n modulo 2 power k, so the last k bits, the answer for every n in that interval will be the same, because by here in the statement, by iterating over I from 0 to n, we find the product of all the values in some interval. One more issue here is that we iterate from 0 to m, not from 0 to m minus 1. So this is not true. What is true is that if m is equal to 2 power k minus 1. Yeah, because then we have product from 0 to 2 power k minus 1. So like, for example, for k equal to 3, it would iterate over all the bits here. Okay, but not necessarily m is equal to that. Of course, if m is equal to, for example, 3 times this value, then we just multiply like 3 consecutive values, because we have product of first 1 million numbers, then next 2 million numbers, and next 1 million numbers, and so on. So the actual solution will be while, or maybe for I from 0, while I times 2 power k is smaller than n, then answer we multiply by something, then something will be pre of something. What to put here? Let's think. We first had n divided by 2 power k. So we have some number n, let's say, and we want to know, we know that the XOR for the first 8 values of I will just change these bits, and what will happen after that. So what happens with I equal to 8, 9, and so on. So it does an extra thing, it changes this bit, and then next bits, and so on. So it just XORs this more and more. So here what we write is, instead of just n divided by 2 power k, what will give index in this array, we XOR it with I. So this basically, this part means the number n without the last k bits, so we've cutted out the last k zeros, and then we XOR it with I, because this is how this part will change. So basically you can think about it as skipping the last k bits, and then by jumping with I every 2 power k, you just multiply, you just XOR this value by 0, 1, 2, 3, and so on. So we have something like this. Okay, but it only is able to compute the values, the products, for consecutive 2 power k values. For example, the product for these 4 values it would be able to find if k would be equal to 2, but if in fact m is equal to, let's say, 6, then we must also multiply these extra few values at the end. So we should do here, what we should do here, let's remove this brute force part, is now iterate over like the last part. So instead of creating I here in a loop, let's remember it. Here we can do while I is smaller than m, answer should be just multiplied by n XOR I, and we increase I by 1. So here, that last at most 1 million numbers we do brutally, just like we did here in complete brute force. So here we know product for first 1 million numbers, next 1 million numbers, and so on, where 1 million just in fact 2 power 20, and here we iterate over the last few numbers. Let's see if it works for examples. It doesn't. We have 0, 0, 0, 0. Why? Okay, so we have a 0 here, so apparently this was what made answer equal to 0. Apparently we multiplied by this, and I think that this for loop isn't correct, because what we want to check is how many full millions we have in M. Like, if M is bigger than first 1 million, then we do something, and so on. But here, for I equal to 0, it will always be true. So for when we start, I is equal to 0, this inequality is true. So for sure, we will multiply answer by pre of something, and that something will be 0 at first for small n. What should be done is here I plus 1, because it means we are at some moment and we ask if the next 1 million numbers fit into M. So let's check now. We got 6, 5000, and the next value is also okay. Let's measure the time. So now I compile with O2 optimization. It's a bit slow. It gave me 2 seconds. So I would want to make it faster. And why is it so slow? Maybe I don't know exactly why it's so slow, so let me check. And for that, let's see if I remove both these parts. So if I comment them, do I get a fast code? Yes, it's very fast. It's like 2 milliseconds. What if I remove the first? What if I have the first for loop? It's still extremely fast. And so apparently this second while loop was too slow. And indeed it's quite slow. So what we can improve here? This loop has at most 2 power k iterations. And of course we can decrease that simply by decreasing k. For example, I can decrease k to 18, just an example, and this will be faster. What is disadvantage of that? Why I can just change here k to 1, because this will be very fast? Of course, because the other part of the solution comes from here. What is from preprocessing. So here, first we have complexity O of m divided by 2 power k, and here we have O of 2 power k. And if we have complexities like this, and we want, it would be good to make them more or less equal, so that no part would be slower, because then it would be better to make it faster a bit. Then it suggests that we should use 2 power k equal to square root of 1 billion. So for k equal to 15, this part would have complexity 1 billion divided by 2 power 15, so something around 2 power 15 itself, something like 30,000, and the same here. So it would be quite fast. We can't do that because here we use the preprocessed values. So here, like preprocessing created, like it jumped with n every 2 power k, so it created 1 billion divided by 2 power k values, per processed values. And we can't fit so many into our code, because we were limited by something like 100,000 characters. In fact, in code forces, it's like 60,000 characters. So this is too small k, but for this value, for k equal to 18, here we get 1 billion divided by 2 power k, so something around 2 power 12 values, so 4,000, and it means 40,000 characters, so it's just fine. So let's do that. Of course, we must repeat our preprocessing. Here I give my compiler, thanks to some flag, gives me warning that I can be uninitialized. Let's see if it's possible. Yeah, right now it's possible because here I create I don't give it some value, for example 1. I should do that. And here I do while I is smaller than n. So it will be undefined behavior. But with this loop, I have here I equal to 0 first. So it should be fine. Okay, it's computed. I have a new long array. I'm pasting it into my code. I can remove the preprocessing part, where of course remove means comment it, because maybe we will need it later. Let's see how fast it works now for the samples. For some reason still quite slow. What is surprising, also answers were changed. So maybe something is wrong in my code. Keep moving forward, asked if, yeah, 1 shifted by k, so this formula in C++ and maybe some other languages means 1 shifted bitwise by k bits, what means for computer multiply by 2 k times. So yeah, this is exactly 2 power k. What is strange here, that still I have running time around 2 seconds, while I expect it to be much faster now. Because I think this part should have complexity 2 power 18. So let's investigate that. What I can write is I can here write what is the value of I. Here the value of I turned out to be 1900, while I expected that I would jump every 1 million. So what is wrong? Here I only changed I by 1, so I meant the number of jumps by 1 million that I already made. And so here I shouldn't use I should multiply it by 2 power k. And let's see. Now it's incredibly fast. It's like milliseconds. I don't remember if my first brute force solution printed this value as well, so let's check that. So I can get back to my brute force solution, remove the so I now declare it twice, remove the fast thing, and let's see the answer now. It's the same, so also 865 something. Okay, so apparently our code is both correct and fast. There will be one more issue, I think, but it's very hard to notice. So here well, I can submit that, and I expect wrong answer, to be honest, because I know my mistake. This was a problem E. And I got the wrong answer. And like, I'm cheating here a little bit because I know a mistake. Maybe it's harder to see here. It's quite hard to see here. What we can do, because we have a brute force solution, it was very easy to do. So we can, let's create a new file for that, not to comment and get back with things every time. I can leave the slow part here. I can remove the pre-processed values. So this is brute force solution. I can run it on sample test to make sure it's okay. Yes, it is. And I can add some more tests here. For example, maybe n equal to 100,000, 100 million, and m equal to whatever. Is it the same? Yes, it's the same. The last new value is. But what we can also do is create a max test. So let n be exactly 1 billion. And I think the statement didn't allow n equal to m. So let's make it 999, 999. And our main solution printed 0. What about brute force? It printed some value. So something is wrong apparently, but it's only wrong, at least this is what we see here, for very big tests. And here, as I said, I cheat a little bit because I know the reason. When we pre-processed values, we only iterated with n up to 1 billion. But when we XOR n with some value I, n can exceed a little bit 1 billion. Let's see on some example. Let's say that the statement said that n is up to 10. Okay, so the biggest possible value of n in binary system is I think 1, 0, 1, 0. So this is in binary system. But when we iterate with I, XORing it with 0, 1, and so on, let's say that I is equal to, I don't know, 6, then n XOR I will be equal, so in binary system it's 6 would be 1, 1, 0. So the XOR of these two would be 1, 1, 0, 0. What is in decimal system? 8 plus 4, so 12. So this value exceeds 10. During a contest it took me a moment to realize that. So actually here we don't only need values up to 1 billion, we need values, like all the possible values n XOR I we can get. And since n is limited by 10 power 30, so 2 power 30 is slightly bigger than 1 billion. And then we know that n we've XORed with some I also limited by that can't exceed that, because both these numbers will have only so many bits, only 30 bits. So it can't be bigger than 2 power 30. So the simple lemma for you to remember is that if some number a is smaller than 2 power k, also b is smaller than 2 power k, then a XOR b is also smaller than 2 power k, because it means a has at most k bits, b has at most k bits, so the XOR also has at most k bits. And it's also true for OR or for bitwise AND. So here let's change that to 1 power 30, so it will be slightly above 1 million. Okay, let's do pre-processing again. This time I wrote it to file out instead of TMP. Let's paste it. I can remove it again. And let's see if now it works for this test, where previously it printed 0. Now it works, and works fast. The answer is the same, 106, sorry. Now I can submit, and I think it should be enough to get AC. What problems am I doing today? I started by showing some problems from our university contest. So we started with some problem about summing XORs. Unfortunately, as I said, you can't access these problems, but what you can do to check if your solution is correct is do what I did. So create a very simple brute force. And just then implement your solution and check if it works fast enough on big tests and if it matches answers with brute force. Then it means it's okay. And the statement for those who want to solve it later was that given two numbers n and m up to 1 billion, these are constraints, compute the product for I, iterating I between 0 and n, of product of numbers n XOR I. So the brute force solution in linear complexity is trivial because you just iterate over I in this interval and XOR, and the actual solution used some particular trick. Hi Richard. How do I select the value of k? Well, I knew that one part will have complexity 2 power k. The other part had complexity m divided by 2 power k, and m was around 1 billion. So then, to minimize the slower part, I should choose 2 power k equal to something like 30,000. So square root of that, because then these two parts both will have complexity around 30,000 operations. What also mattered was the size, the number of pre-computed values, because right now my code has size 43 kilobytes, so it has around 40,000 characters, and I couldn't fit much more. So I can choose smaller k, even though k equal to 15 would be, I think, perfect in terms of running time. The complexity would be best. Can you plot, give a link to the PDF with the problem statements? I don't know if I'm supposed to. I don't know if I should do that. It's a private contest, so I'm not forbidden to show problems, but I'm not sure about, for example, sharing the exact PDF with other problems, for example. Okay, so regarding other problems, I think f is also valuable, but I will not implement that problem right now. The statement of f was a bit more complicated, but was something like this. We are given two strings in the input. Let's say that the first one is longer, and the length of this first string is up to 50,000, so a bit smaller than usual 1 million or 100,000. And we are given a shorter string with length 100, so this is big and small string. And a simple problem would be find the number of occurrences of the small string in the big string. But actually here we have some queries that we should answer. Each query of the following form. We are given two indices in the big string, for example maybe index of this letter and index of this letter, and we know that so given this first of the two indexes, someone will choose a random index in this prefix. For example, maybe it will be this place, and we'll just have this prefix, the remaining prefix. It will, let's say, stay alive. So when we are given for example, in the input, so it represents this place, then we say someone will generate a random index between 1 and 4. Let's say that it will be 3. And we are only left with prefix up to this place. Sorry, up to m. So if the first number in the query is 4, then we will either have prefix I, or IA, or IAM, or IAMN. Something of these 4, each with probability 1 divided by 4. Okay, and we'll also in a query given the second index, here it was 7, so here. And the same thing happens with a suffix. So somebody will generate a random index between this given value and the end, and only this suffix will stay alive. So for query 4.7, there are 4 possible prefixes and 2 possible suffixes, so there are 8 possibilities. And for every possibility, we glue together the prefix and suffix that were alive. For example, maybe it will be IAM SB, or just AB, or ASB. And in that glued merged string, we ask about the number of occurrences of this small string. For example, in the first query, where let me think a moment. In the first query, if the prefix was IAM and the suffix was SB, then we indeed have an occurrence of the small string. But if the prefix was IAMN, then SB, we don't have an occurrence, because an occurrence means a substring that exactly matches the small string. One more example is that, for example, let's create a new directory for that. So the first problem was with source. The second problem was with strings. For example, if the small string is AA and big string is something like this, and if then what is alive is this part, so the last 2 b's and the first, let's say, 5 characters, then what we have is these 5 characters and BB from the suffix, and the number of occurrences is 1. If this glued string contained 3 A's, the number of occurrences of small string would be 2, because this is one occurrence, sorry, this is one occurrence, and this is a next occurrence. Okay, the question is, for every query, given this limit for size of prefix, so 2 numbers, limit for size of prefix and size of suffix, iterate over all possibilities. As I said, there was 8 possibilities here. For each of them, count the number of occurrences of the small string and print the sum of these numbers of occurrences over all possible something times something possibilities. Hi, no moniker. Coach of October challenge is on. Okay, possibly challenge meaning the 10-day contests. Well, then for sure I will not talk about those problems because it's from an ongoing competition. But of course, do participate in those. In that, a long contest, a contest lasting to 10 days, has an advantage that they can use some hard problems for which you have a lot of time to think about solutions, what is very cool and unusual because usually you only have like 2 hours. Okay, back to a problem. How to solve this problem? So constraints once again were big string 50,000 length and small string 100, the number of queries 50,000. Okay, let's say that we're asked, let's say that in a query we know that we'll choose some prefix up to this point and some suffix starting from this point. So here there would be like 6 times 3 possibilities, so 18. And we wonder what is the number of occurrences of AA in each of them. Okay, first we can find occurrences that will be present in just the prefix. For example, in whole, if whole ABBAAA will stay as a prefix, then there will be 2 occurrences. And the same with suffix, but here there would be no occurrences of A. So for every place we can do some pre-processing. For every place we should find out whether the small string occurs at this place. It's possible to do in plenty of ways, for example with KMP algorithm or with hashes, or because constraints are very small here and we can have complexity size of big string and size of small string like times, because 50,000 times 100 is okay, then we can just implement dynamic programming in complexity nm, and so in every place, starting from, well, not even dynamic programming, just greedy, like obvious greedy algorithm, starting from every place, we want to find out whether the small string would occur. So just iterate one by one, and for every starting place we have complexity 100, the size of small string, so the total complexity will be of n times m, what is fine. And if we know where there are occurrences of AA, then we should compute something a bit harder. So here, for a query like this, so choosing random prefix here and a random suffix here, what is the sum over the number of occurrences? Well, we have this AA. In how many ways, among 18 possibilities, it will be present? Where here we must either choose this prefix to make AA be inside, or this prefix. So among 6 possible prefixes, so starting from this one, so A, B, and so on, only two last of them are okay. So there are 2 ways to choose a prefix to make this A be inside, and of course all 3 ways to choose a suffix are okay. So we have 6 ways here, and the next possible AA is here, and it's inside only one prefix, the whole thing. So to the answer we should add 1 times. Suffix can be chosen in all 3 ways. So this AA occurs exactly 9 times. So we should add 9 to the answer. And generally, what we want to do for a prefix is to know whether this is a good occurrence of the small string, and if yes, then add it multiplied by 1 to the answer, and also multiplied by size of suffix. Then, if this is a good occurrence, then you should multiply the size of suffix by 2 and add to the answer. The same here but multiplying by 3, 4, and 5. And this 5 means there are 5 ways to choose a prefix to make it contain this substring. But here, of course, this isn't equal to the small string. And it would be too slow to just check every substring like this. This is why we have preprocessing. And with this preprocessing, we should know an easy thing to compute is the number of occurrences of the small string in some prefix. This is easy because we first run that algorithm to find all the occurrences and then apply prefix sum to know in the prefix what is the number of occurrences. But here we want to count occurrences here with multiplier 1, here with multiplier 2, multiplier 3, and so on. So there are 2 ways for that. Either do some more complicated structure to be able to answer in some interval about some value times 1 plus next value times 2, next value times 3, and so on. It's possible to be done. But here, since we can first do some preprocessing and then answer queries, and not just online answer queries and do some changes, we can simply do the following. If we know the answer for this prefix, the answer meaning the number of occurrences of small string with those multipliers, then when we move to a bigger prefix, and of course this is before all the queries, so we have the whole big string and we just go prefix by prefix. So if we know that the sum of those occurrences of A is, let's say, X here, and the number of those occurrences is Y, then when we move from one prefix to the next prefix, the answer, this sum with multipliers, will be changed to X plus Y, and the number of occurrences will stay the same, unless when we move to the next prefix, so here to this one, we get a new occurrence of the small string. So here we would, from a pair X to Y, we would move to X plus Y plus 1 and Y plus 1. So maintaining these 2 values, it's very easy to go prefix by prefix, and then after that, when we have a query, we know for a prefix what is the sum of the numbers of occurrences with multipliers, and we add it to the answer multiplied by the size of suffix. So we solved one part of a problem. Will I participate in the Codeforces round? so we can discuss that after the contest. But I doubt I will have time after the contest. I'm doing stream now, so I will not do some, I don't know, post-contest discussion. Maybe I will just read or write some comments in the Code Forces topic. And good luck to you, Rishabh, in the round. Thank you for doing this. You're welcome. I'm glad some people like this stream. Okay, back to the problem. Okay, the harder part of a problem is to notice, like noticing it is easy, dealing with it is harder. When we glue the chosen prefix and suffix together, some new occurrences of the small string can happen in between. So maybe this string, well, let's start with this thing. So maybe we'll choose some prefix and we'll take like some part of the small string will occur at the end of this prefix, because maybe, for example, here we would have ABBA. So here there are no occurrences of AA, of course, but if we also choose this suffix, then we have then ABBA plus ABB, so in total it's ABBA, ABB. We have an occurrence. So what we do? For of course this small string could be a bit longer. We iterate over which part of the small string would be in the prefix part, and the remaining part must be in the suffix. So now let's consider this this possibility. Also later we'll have to consider this one. So here we are interested in the number of strings here that end with string like this, and similarly for the suffix we are interested in the number of suffixes that start with AB. And later the same we will do now for the other possible like division of the small string into part from prefix and suffix. So for example here, what should be added to the answer? What is the number of prefixes here that end with AA? Well, this is one, and this is a second one. So there are two possible prefixes ending with AA, and here there are two suffixes, BB and B, that start with B. So for example, taking BB from here and, I don't know, this whole prefix would give us the small string when we glue the two parts. So this is the logic, and how do we implement that? When we did those prefix sums, so we said that in the first part we computed the number of occurrences of the small string for every prefix, the same for suffixes. We can do the same actually for every part of a small string. So when we have some small string and a long string, we can do dynamic programming, or let's call it like prefix sum of size n times n. N is the size of the longer string. So for every prefix here, what is in the first dimension, and for every prefix here, we would know here what is the number of prefixes of that would end with exactly this string. And this is like doing it while implementing the first part, the one about just finding the strings, the occurrences of small string here. It's basically the same thing, because here when we start from every place and we see if we get an occurrence of this, for example starting from here, let's check if we have the whole AABBA. When we move to the right, in every moment we know if we have some prefix. For example, when we got up to this place, we know that we have an occurrence of prefix AAB here. So we increase this value by 1, we say yes, we have an occurrence here, and then we apply prefix sums. And the same should be done for suffixes. Either you should implement a very similar code or you should reverse strings and then apply the same thing, so use the same function, the same code again. Okay, and then we must somehow combine them. So just when we have a query about some prefix, some suffix, iterate over a way to divide the small string, and add to the answer, add the product of prefix sum here for this prefix that you chose in the small string and suffix here. The total complexity will still be n times n, so this is the preprocessing, times answering queries, and in every query you just iterate over the way to split the small string. So we have here q times m. M is the size of small string, so 100, and this is the intended complexity. Okay, so this looks like sometimes problems with strings are very hard and require complicated structures, like, I don't know, suffix trees or arrays, but here it was just things like dynamic programming or very simple, like greedily checking if something is a substring. Will I participate in code, Jeff? I don't know. I don't know if I have enough time to spend like hours thinking about problems. So I doubt it, to be honest. When I don't have much time, then 2-hour contests are better for me. Okay, do you have any questions about this strings problem? And I will try to find a new problem. I don't know if you will be happy about that or not, but now we'll do some geometry. And again, I will not implement it because it would take a lot of time, but I think it's valuable to know a solution for a problem like this. And while solving, we will see that the main part about logic is not really geometry. It turns out to be something connected with segment tree or intervals. So let's see. Okay, what is a problem? A problem is you are given, well, I will do some drawings. A problem is give on the plane. So let's say we have some plane. This is x coordinate, x axis and y, and we are given a rectangle, isothetic rectangle, what means that for example like this, what means that, maybe this will be a better example, sides of this rectangle are parallel to like axis, so a rectangle like this is impossible. So it's a nice rectangle, and we are given n lines. Each line has form y equal to ax plus b for some given a and b, So lines are like this. Okay, and the question is, maybe one more here, given n lines, n is up to 100,000, well, we are asked to count the number of pairs of lines that intersect inside the given rectangle. So let's count the answer here. For example, this intersection doesn't count because it's not inside the rectangle. And the statement said we also count those on the boundaries. So here this one counts. It's exactly on the boundary, but it counts. So here we have second one, third one, 4, 5. Oh, sorry, these are not. We count how many pairs of lines intersect. So this, we don't have two lines intersecting. We have just a line intersecting with rectangle. We count pairs of red lines. Here, here. Also, also here. And so we have 1, 2, 3, 4. We don't have, the answer isn't 5, the answer is slightly bigger than that, because we don't, the question isn't about the number of points where lines intersect. The answer is how many pairs of lines intersect inside the rectangle. So here we have a few lines intersecting in one place, and for example these two lines intersect, so they increase the answer by 1 because of their intersection here. But also these two lines also intersect, so we have like a second intersection, and also like this line and this line, I think I didn't count. Anyway, so here, here, and here, but here we have actually 3 pairs. Generally, where if at some point there are n, or let's say a lines intersecting with each other at one place, then we'll add something like a times a minus 1 divided by 2, I think, because this is the number of pairs. Okay, any questions about the statement? Do we have? Also, there are some constraints about the coordinates that are quite big. Some numbers, some coordinates are up to 1 billion, what is fine, but some coordinates, for example, the upper and lower side of rectangle, their coordinates are up to 10 power 18, and also like for these lines given as ax plus b, also that b is very huge, very big, like 10 power 16. It makes some troubles in implementation. We will talk about that later, but right now we will not focus on details like overflows or precision. So first, let's just solve this problem in any way. Let's make sure that the logic is done first. And how to solve a problem like this. Of course, it isn't enough to just iterate over pairs of lines, because the constraints don't allow us to. N is up to 1, the number of lines, n, is up to 100,000, which is too big to have complexity n squared. What else we can do? We can do something like when we are given points or lines, we can find convex hull, something like that, but it doesn't make sense here. Like for example, if we say that there are there are some lines that are, I don't know, outside and they cover everything, so then they create a convex hull. It doesn't matter, because it doesn't say anything about the number of intersection of lines inside. So the only other thing we can do reasonably in time is finding intersections, or counting, but well, we can find them, finding intersections of lines with the rectangle. So let's put blue color for that. So we have an intersection here, here, and so on. This is what we can find, and the complexity of that will be oven. It's also here, but I don't want to spoil drawing. So we can find those intersections, and actually those create some pairs. For example, we have one pair here, like these two intersection points come from the same red line. So yeah, this is a pair. Also, for example, this is a pair because it comes from the same line, and so on. So actually we can say that on this rectangle we have some pairs of items, of elements. So we can put, let's, I don't know, number them to see that they're in pairs. So this pair will be described by number 2, that one with 1. I don't know, here we have what else? Here we have 3, and now it would be 4 and 5, but here we have the same place. But well, let's deal with that later. Okay, and now a crucial observation is to say that the positions of those numbers, positions of those pairs, are enough to say which lines intersect. Because we are on some rectangle, we could also say that we are on a circle, and there are some pairs of points connected. For example, this point with this point. And now we say that two pairs intersect if and only if on this like rectangle or circle those pairs are like alternatively, like oppositely to each other. I don't know how to describe it well, but where two elements are at some places, for other pair to intersect it, one number must be on like one side and the other number must be on the other side. It doesn't necessarily mean that it must be on this side of rectangle. This one could also be here, for example. Just an important thing is that with respect to this line, one element would have to be somewhere here, and the other element would have to be here. And this becomes a problem that doesn't have any geometry from this point, when we already found the points of intersections. Because we're given a sequence of numbers on, let's say, a circle, we can say that, and we are asked about something similar to the number of inversions in a sequence, but this time we're given a sequence of numbers, each number occurring exactly 2 times, and we are asked about the number of pairs of values such that they are in like this relation. So on one number, one pair is on 2 opposite sides of a line connecting the other pair. A good line sweep problem. I wouldn't call that line sweep problem. We don't really move with some sweep line, but there are similarities. Well, we have a lot of lines here. So here, for example, we could say now that the input, like for our new problem, what becomes is we're given a sequence of numbers, for example, 1, 3, 4, 2, 5, 1, 4, 5, 3, 2. Let's later deal with the fact that some places have two numbers at one spot, but for a moment maybe let's assume that this 5 is here to make things easier for us. So we are just given a sequence of two n numbers, each of n numbers occurring 2 times, and we are asked about the number of intersecting pairs. How to do that? Well, let's see this example. 1, 3, 4, 2, 5, 1, 4, 5, 4, 3, 2. Okay, what we can do? We know the connections, like for example this one is connected with this one. And what we do? If we say that this pair is connected, now for every number here, if it's connected with something that is outside, like later than this one, for example this 4 is connected with 4 here, then we add 1 to the answer. So basically up to this moment, for every number, if we know where it's connected, and we just know that if it's connected to something here, it gets +1. So a solution is start from the left. For every number, see where it's connected to. So it's here in this at this. Right now it's here. Here, say that everything being connected to this place gets +1. Right now we don't increase the answer. We just will increase something in the segment tree. Just we say that everything that will be connected to something here gets +1. Now we consider the next number. We see where it's connected to. It's here. So from segment tree we read that the answer should be increased by 1, because we notice that this way we notice that 1, 1 is intersecting with 3, 3. What is also true here? Let's see. 1, 1 on the drawing was intersecting with 3, 3. Okay, so we added +1 to the answer. Now 3, we see, since it's connected here, we say in segment 3 that this interval would get +1. Now we have this 4. It's connected with this place, so we see segment 3 says the value of this place is 1, so answer is increased by 1. And again, some interval gets +1. Here we have +1. And so on. And for example, in a moment 2 is connected here, so it would get, I think, +3 to the answer, because in segment 3 this place has 3 in segment 3. And let's see that 2 indeed intersects with 3 lines. 1, 2, 3. So all of that is possible to get with a segment tree that just supports operation add something to the interval and give me the value at some place. so it's quite easy segment tree. Also, when we get to the second occurrence of a number, so here it was that, we should remove this +1. So we should, to this interval, subtract 1. Because now for every future elements that are connected somewhere to the right, they don't intersect anymore with 1s. Because we just said that up to this moment, for every element starting here and ending to the right, it would get +1. So here later, for second occurrence of 1, we'll put -1 here on the suffix. Depending on your implementation, possibly each intersection you will count twice. It depends. So whether where you consider some number and then you add something to the answer because you noticed this number has some number of intersections with others, but if when you consider those other numbers, if then you also add because of intersections, then each intersection you will count twice, because this intersection between lines 1 and 3 you will count once when considering element 1, and the next time when you consider element 3. So it depends on the implementation. Maybe you will have to divide the answer by 2 at the end. Okay, and if you think about that, the fact that here 3 lines intersected, or more lines intersected at one place, doesn't matter, because we just, with this algorithm, we just, for every line, we basically count the number of other lines that intersect, so everything will be okay. And the remaining thing is to deal with this special spot, because we don't really know how to order things here. So whether we should put 4 or 5 first in the order. And it does matter, because notice that if 5 would be like lower, then we would get something like this. 5 would think that it connects, let's say, places like this. 4 would connect places like this. So there would be no intersection between 4 and 5, while there should be. So there are 2 ways to deal with that. One way is to imagine that this rectangle is slightly bigger. So maybe it's in fact something like this. If you imagine like extending this rectangle by some epsilon, then there would be no ties anymore, no places where 2 lines intersect exactly at the boundary. Because for this example, where lines 4 and 5 intersected exactly here, for this given x value, when you, instead of x given in the input, consider x, for example, x minus some epsilon equal to, let's say, 1 divided by 10 power 15, then there would be no intersections at all, like at one place, and the answer would be counted correctly. Because if we, in the initial rectangle, if we count intersections inside or on the boundaries, then by extending it just by a little bit, just like tiny epsilon, then you can say we count those intersections that are inside, because intersections that were first on the boundary are now just inside the rectangle. Of course, in geometry problems it's better to use integers, because otherwise you would Well, with some precision issues, you could make some mistakes. For example, not say correctly whether something is inside or not. So it's better to stay with integers. So when I said we imagine extending by epsilon, we indeed just imagine that. We don't actually change x in our code. But thanks to that, we just know how to sort things. When there is a tie, like this one, we just say whether to the left which line will be will be lower and which one will be higher. So here we see that line with 5 is higher, just to the left, so we put 5 above 4. So we just imagine extending the rectangle. So that was one way to deal with the issue. The second way is to not really produce a sequence like that, but to produce a sequence and to know that these two numbers are in the same spot. So here it would be basically a list of lists, or you can think about it as like a sequence of buckets. And here 4 and 5 are in the same bucket, in the same list. So we know that they're in the same place. We should increase the answer by something like this, because like when we know that there's a lines intersecting each other at this boundary point, we increase the answer by this value, and then we just must be careful not to count any more intersections between them. Like we consider them in any order, just first counting intersections of those with other lines that were already present, and then processing them again, just like a moment later, to apply those plus ones on intervals. What we must be careful about, not to count again intersections between them, because then we would have to care about the order. And in this problem there are some extra issues. For example, possibly there could be lines like this that only intersect a rectangle in one place. So there is a special if for that. Also, you have to carefully sort the events, the intersections, blue intersections around the rectangle. Like it's hard to implement that because among the top segment you must, for example, sort from left to right, then to the bottom, then to the left, then up. So you can just, for example, sort by X. It's harder than that. And the last issue, I kinda got lost how segment tree is used here. Well, so later, first try to solve a very easy problem but use segment tree for that. So just given a sequence, count the number of inversions. If you don't know what inversions are, you can Google that. Actually, I think you will be able to find a problem that you can submit. So the inversion in a sequence is a pair of elements where the second one, the later one, is smaller than the first one. So try to solve the problem with inversions first, and then go back to this problem where we are given pairs of elements. It's a similar thing, just this one is a bit harder. Okay, and the last issue in this problem is that coordinates are huge. And we can't do everything on integers. When we count these places of intersections, for example, let's say here, we have some line that has with formula y is equal to ax times plus b, something like this. And when we want to find this x value, so the intersection point with top segment, so we know this value y from the input. Then we know that here we must have something like we want to find x, so it's y minus b divided by a. So this is not necessarily integer, and if it's to solve this problem correctly, you must use integers. You can't just compute it as a double or long double, because the numbers here are huge and they are too big to rely on precision. You can't then compare which of the two numbers, if they're close to each other, which one is smaller, or whether they are equal or not. So you must, to solve it correctly, you must store this as a fraction. You store this as a pair of numbers, like numerator and denominator of a fraction. And then when you have two fractions, so let's say a divided by b, c divided by d, to compare them, so for example in sort, when we want to know if a divided by b is more than c divided by d, we can actually, to avoid now division, we can compare also moving d to the left side and b to the right side. We can compare a times d, whether it's more than b times c. So here we have integers, and an issue is that here we have 10 power 18. So multiplications of numbers of this magnitude don't fit in integer or in int type. You are fine if you use Python or Java. Well, then the solution would be slower a bit, but it's fine. Depending on computer architecture, maybe you will be able to use, I think it's used like this, int 128. You can't use that in code forces, but for example I think in IOI or ACM finals you will be able to. So this is basically long, but even bigger, with 128 bits. So by casting your numbers to this type, you can now correctly compare these two values. You can do the multiplication. It will not exceed, it will exceed long. It would give you overflow, but you will be okay with this thing. Unfortunately, it's impossible to use in code forces, because code forces uses Windows, and int 128 is not supported. So you must do some other trick. And one possible thing, I think the easiest one here, was to not really do the multiplication here, but to represent, for example, let's say that we have 1000 divided by 300, whether it's smaller than something. So we can represent it as 3 plus 100 divided by 300, whether it's more than something. So we can get the, how is it called? Integer part, plus some fractions more than 1. And in this problem, actually, where when you find these fractions, it will turn out that b and d, those came from here x value and a value, and they do not exceed 1 million. And a and c can be here huge, but thanks to writing it like this, you get rid of this huge number. And if you, for example, get, I don't know, something like this, now you can easily compare, because you first compare the integer part. Here 4 is bigger, so we know the answer. But if integer part would be the same, then we are left with fractions. but this time the values are limited by 1 billion, so you can do from this you can do A times D, whether it's more than B times C. So here it would be 100 times 70 moved to the left side, whether it's more than 300 times 50. Also, I think it would be possible to, by the way, apply something like how is it called, the algorithm for this GCD, Euclidean algorithm. So then we could compare instead of that whether 300 divided by 100, whether it's bigger than this, but this is just some interesting fact. You shouldn't use it, and it adds extra logarithm to complexity. Okay, so yeah, this is the best solution, I think, to this issue. But if possible, you should use int 128. Also, you could actually implement your own int 128, and let me do it here, because it's very easy just to do multiplication. Big integer in Java, yeah, so as I said, in Python and Java you're fine, but program will be slower because C++ is faster. And the whole implementation is very long here, so if C++ is your best language, then I don't recommend here to like switching to some other language. Okay, so let's say that we want to implement our own type, very simple type. So given two numbers, A and B, let's later think what exactly I want to do, but given two numbers A and B, I want to return them in some form, some type representing int 128. So actually let's also return a pair of long longs, and let's see what it would mean. Basically, when we, for example, in decimal system, when we multiply 7 times, I don't know, 4, we get 28. If we only can use digits, so here digits represent here my long type, I can use long. Here I can, let's say, use digits. But how to represent 7 times 4 if we only can use digits, single digits? This type, let's say this number is too much for us. Then I can represent it as a pair, 2 and 8. And if I have a pair like this, I can compare two pairs. So here what I want to do is compute A times B and return in form xy such that A times B is equal to x multiplied by 2 power 64 plus y. So this is like the big hard version of this. We do the same thing here. Given 7 and 4, we can find the two digits here. We do the same here, just base is very big instead of 10. Okay, how to do that? Also, we know from here that let's say A is up to 10 power 18, B is up to 10 power 9. Okay, so what to do here? Actually, let's use a bit smaller base, because otherwise we would not be able to do any multiplication here. And let's create what we want to return, or maybe So we want to find these values x and y. X is, let's just first find a in this form. This is very easy because it's just a divided by 2 power 32 and y is a modulo that. So we already achieved this part. But now we want to do the whole thing with a times b. By the way, in C++, instead of this, you can write things a bit like easier. This also can be written as a shifted by 32 bits. This is equivalent to, so we could also write x is equal to that. And here we could say that it's something like, for example, y is equal to a shifted by that, shifted back. So this means divide by 2 power 32. This means multiply. So with this operation we set the last bits to 0, then minus a minus that. This is some bitwise tricks, or we could just write a and 2 power 32 minus 1. This is a number that has the last 32 bits set to 1. By ending with that, we just get the last 32 bits. So it isn't very important. This is also fine. When we do, usually division and modulo are slow in C++ and other languages, but compiler will make it faster when you divide or multiply or modulo by a power of 2, because compiler will itself understand that this is equivalent to something like this. So compiler will do job for you, so don't worry. When you, for example, divide by 8, it will be faster than if you divide by arbitrary number. Okay, so we represented a in this special form, and to get b, what is enough to do is to multiply those by b. Here, when we represent in this format, we want this to be the smaller part, something smaller than 2 power 32. So we want to, because otherwise this format would be not unique, and we couldn't really compare the two values. Like, because we do all of this to compare the two products, to know if a times d is smaller than b times c. Okay, so here what is left is to do what is always done in big integers, or just when you multiply, when a human multiplies two numbers, for example 57 times, I don't know, 15, then what you do is you compute first digit. For example, here it would be 5, because it's 5 times 7, and then there is some part that moves to the next digit, and the same happens here. You to the next digit, to x, you add y divided by 2 power 32, and y, then you can do modulo 2 power 32. And this is what I used in this problem to compare the two products, like here, like this. So then we would write, when we write a comparator to compare if a divided by d is smaller than c divided by d, we just write return f of ad is smaller than f of cd. Sorry, cbc. Like it means comparing these two products. And one common mistake here when you transform an equality like this is that you should know from math lessons that when we multiply two sides of inequality by some number, for example by d, to move d to the other side, we change the sign of inequality if that number was negative. So what is a good thing to do to make your life easier is to first do something like this. If b is smaller than 0, then multiply both a and b by -1 and do the same with d. Of course, this operation doesn't change the value of a fraction, because you can multiply both numerator and denominator by the same value. But thanks to this, now you can assume that both b and d are positive. And this can only help. So when you use fractions that you implement yourself, I recommend in constructor, in the moment when you create a fraction, a pair, check if the denominator is smaller than 0, and if yes, then multiply both by -1. What of course doesn't change the value. So yeah, that was a bunch of random stuff. And that's about it. I think it was like, we didn't solve many problems, but I hope you saw a lot of useful techniques here in those few problems. Let's see if something else here is easy to describe. Okay, we have one problem that is, I would say, combinatorics. So let's say counting the number of permutations that satisfy some condition. Or we can do something that is more related to graphs. So your choice, guys. Let's do some small voting. Either graphs or combinatorics. The difficulty is similar, I think. Combinatorics win unless we get more votes in a moment. Also, if you want to, can suggest something for the future. What do you think the next streams should be about? But we will here solve combinatorics then. So a problem. It might be hard to understand the statement. So I will just say what it turns out to be about. We are given a sequence of numbers of size n up to 1 million. Let's say that this sequence is 1, 5, 2, 5, 3, and we say that somebody will generate a random new sequence of the same length where every number will be random number from interval 0, 1, between 0 and 1. So some real number, for example, I don't know, 0.7209, something like this. Random real number from this interval. And we are asked about, in fact, let's say, probability that this sequence will be similar to our given sequence in the input. And what means similar? It means the following, where when we write the new sequence here, so it has the same size, let's move numbers so every number would be below the same, like the same index. Okay. So we have sequence in the input 1, 5, 2, 5, 3, and let's see what it means that a new sequence would be similar. We got one more vote for graphs, what makes it a tie, but now it's too late. And I also, by the way, prefer combinatorics. So the similarity means for every interval of indices, for example, for this interval or for this interval, if we find the biggest number in this interval, breaking ties by taking the first number of them, then in the second sequence we would get the same place. For example, here in this interval the biggest number is here, and here again this number is here, so it's okay. But when we take a look at this interval, in the first sequence the bigger number is here, so index 4, and in the second interval biggest number is here, index 5. So these two sequences aren't equal. But if I change this value, like if I swap these two values, now it is in fact similar. Because we can, well, check all the intervals. For example, this interval here, both here and in the next sequence, here is the biggest value. Also, let's remember, when there is a tie, then among the tied values, we choose the leftmost one, so the first one. Here, then in this interval, the biggest value we say is here. And when we take a look at the same thing in the second sequence, it's here. And you can check all the intervals here. If I'm not mistaken, we are fine. And the question is, well, the statement says something equivalent, but the general question is, what is the probability that this new sequence is similar to the one given in the input? Yeah, so the input contains size of sequence n and the sequence itself. So this is the example input is this, and we want to print the probability. What about combinatorics plus graphs? Well, it was either that or that. We are asked about probability. And this example shows that it isn't necessary that for every two numbers, if one number is bigger than the next number, then the same must be true in the second sequence. Here we see that first number in the second sequence is bigger than the third one, but it's the opposite in the first sequence. But if that was true, that we would just want the numbers to be in the same order, I claim that the answer would be just 1 divided by n factorial. Because here we have a bunch of random numbers in some interval, 0, 1. We can say that the probability that some two numbers will be equal is 0. So, because if you generate two or bigger number of random numbers in some interval, those can be any real value in this interval, the probability is extremely slow. It's in fact equal to 0. What doesn't mean that it's impossible. So it's a bit it's counterintuitive. It's very strange to think about that. But the probability we can say is 0. Because, for example, when we already generated random number 0.25, if you again generate interval 0, 1, there are so many values, well, there are infinite number of values, that the probability of getting this again is 0, because it's like 1 divided by infinity. So we can say that we can assume that all the numbers here will be distinct. So then if we just wanted the same ordering as here, then the answer would be 1 divided by n factorial. But this example shows that it isn't true because of these two values. Also, it isn't a big deal that here two numbers were equal, because the statement said ties we resolve by index, saying that the first number is bigger. So we can just say that here we order first by value and then by index. So basically here we can change this 5 to 4, basically, when sorting numbers from the biggest one. What it means, we can assume then that the input has distinct numbers, and we know that here each of n factorial possible ordering, which number will be the biggest, will be the second biggest, and so on, each is equal probability, because like everything is symmetric. So the question is here, what is the number of orderings of factorials that of permutations that say which number is biggest, second biggest, and so on? What is the number of permutations x that generate a sequence similar to the given one? And we will just print x divided by n factorial. And this will be the answer. Hi, I just joined in. Can you share link for the problem statement? Hi, Tushar. I will not share the link because it's like, let's say, private university contest, so it's not open. Well, later you will be able to watch the whole stream, so you will be able to see the statements. The current one is given a sequence, we generate a new random sequence, and we want to find the probability that it's similar with some definition to the given sequence. And similar means for every interval of indices, if we find the biggest number in the first sequence and here also the biggest number in the same interval, we will find the same place. And you have the formal statement here on the left. Okay, so we said that the question boiled down to count the number of permutations. So now we just have this sequence, count the number of permutations that are similar to the given one. So, for example, of course, the same permutation will be similar to itself, but also this one will be similar, and a few others. Actually, here I think the answer would be 6, if I'm not mistaken. For example, this one would be also similar. You can iterate over intervals, like this interval is similar to this interval. This interval here, biggest value is here, and the same here. This is also true here, here. So it's fine. And there will be, I think, 6 permutations like that, because in this exact case, you can order numbers 1 to 3 in whatever way you want. Why? Because let's see which numbers, when we, for example, take a look at 2 adjacent numbers, I claim that in these permutations we count, in all the permutations that are similar to this one, if we take a look at 2 adjacent values, here in any similar permutation, they must be, the order of them must be the same. So in every permutation, this number should be bigger than this one. Why? Because when we take a look at this interval from definition, in this similar permutation, also here must be the biggest number in interval. So this value must be bigger than this value. But for example, we noticed here that it isn't true anymore for these 2 values. It's okay if this is, as we said here, it's okay if 2 is on the left and 1 is on the right. Let's try to understand why. Because when we have an interval that contains these 2 numbers, so we would maybe be able to distinguish between them. So it could be this interval or this interval, this interval. An interval that contains both 1 and 2, like both index 1 and index 3, then between them there is something bigger. So no matter what is the value of those, the exact value of those, anyway, for each of these intervals containing them both, the value that is the biggest in the interval will be something else. So we can't distinguish between them. In no case there is an interval where it contains both of them and one of them will be shown as biggest one, so bigger than the other one. What means that we can like swap them and it would be okay still. And generally, so for 2 numbers, we can distinguish them only when between them there is no number that would be greater than those 2. Because then, for once again, proof is, if there, for 2 numbers, if somewhere between them is a number that is bigger than both of them, then for every interval that contains these 2 numbers that we want to distinguish between, a biggest value is something else. None of these 2 values can be the biggest one for an interval that contains them both. This is a claim. Okay, and so this is some observation. Let's change it into algorithm, something that we can implement, and later let's see how to implement that. Okay, so there is the biggest value in the whole sequence. So it's kind of reverse thinking, I would say. One solution would be to iterate over pairs of numbers, and for each pair to check if there is a bigger number in between. But this way you can't achieve complexity faster than n squared, because in particular you must iterate over pairs of numbers. Since n is 1 million, we can only iterate over one number. So it makes sense, of course, to think about iterating over one number and thinking, okay, let's try to, in a kind of fast way, process all the pairs of this number with some other number, but this approach turns out to be bad. Instead, what is like, there is one number that we can iterate over. It would be that bigger value that that doesn't allow those two on the sides to like know each other, to distinguish between them. So actually we can iterate over, so consider each value, maybe starting from the biggest value. And okay, so we have a 5 here, the biggest value in the whole sequence. This 5 means that we can't distinguish in any way values of these numbers and a value of this number. So I was wrong when I said that the answer is 6, because from this also we know that, for example, this is a valid permutation. Here the first number was 1, but it doesn't matter much because it will never be compared with something on the right. So it could also be 4. The only important thing is that it's more than this 5. So when we consider 5, we say that these 3 numbers don't matter with respect to this one number. So the only important thing is that this number in the sequence we generate randomly, or in this permutation, random permutation, should be the biggest one. What is the probability of that? It's 1 divided by 5. It's the probability that in a random permutation, the second number will be the biggest one. Or in a random sequence, where every number is from interval 0, 1, the probability of the fact that second number will be the biggest one is 1 divided by 5. Okay, so this is, like, let's say this is fixed already. And now we know that, so this is fixed. Here, the next biggest value is 4. We know that it's the biggest value in this interval. Like, we know that it must be bigger than this value, because we can compare between them. But we can't compare between this and this because of this bigger value between. So here what we say is that in this permutation, this should be value that is bigger than anything here. And what is the probability of that? Well, it doesn't matter what we chose here. The probability of the fact that this is the biggest value here is just 1 divided by 3. So, and then we fix this value, and then we move to the other question mark. So the next biggest value is here, it's 3, but it isn't compared anymore with anything. So we just multiply the answer by probability that this number is biggest one in this interval of size 1. So the probability of that is 1. The same here and here. So basically we do something like this, and each time we have some interval that is not yet fixed. So we know that some number should be biggest one in this interval. First it was interval of size n, and we just multiply the probabilities of that. And that's it. This is the answer. So the solution is sort numbers, just to know where is the biggest one, next one, and so on. So the permutation was 1, 5, 2, 4, 3. So sort numbers to know the order of indices. So at index 2 we have the biggest value, then we have index 4, index 5, and so on. And in this order, we know that this is the biggest number in some interval. We multiply the answer by 1 divided by size, and we move to the next index. And so to know what is the size of this interval where our current number is, what is how to do that in implementation, I recommend using set. So like for, let's say, forbidden positions, something like that, set of ints that would store where those x's are. Also, for convenience, I recommend, let's call that set just s, or positions. For convenience, I recommend starting the program by inserting here something like this. Let's say that indices are 1 through n. Then we put a fake x at the beginning and end. And now, every time where we are looking at some number, then here in set we use lower bound and upper bound to, in logarithmic time, to get the next x and the previous x. And thanks to that, we know what is the size of interval. And this is the whole solution. The total complexity is n times log. Log because we used set and sort. And one like interesting thing to know, to be aware about, is that actually we can avoid this log from set, assuming that numbers are already sorted, and it's like a common technique. So where we are given a sequence, and in some order we will turn off some places, and every time we want to know where is the previous and next x, so a number that is already removed, we can do that avoiding set at all. Of course, it isn't necessary in this problem. So usually n log n complexity is fine if size of input is anyway n, because reading the input is usually slow, so using set with that complexity doesn't hurt more. But sometimes you will want to make your program a bit faster. Sometimes you will want to remove one log from complexity to make it a bit faster. So actually it's possible to do the same thing in linear complexity, but by doing the same in reverse. What does it mean? So we had a permutation 1, 5, 2, 4, 3. Then we turned numbers off, so we removed them in this order. And actually, if we start from this state and we do the same thing in opposite direction, we don't need set, and we are then fine with two-directional or maybe bidirectional list. So I'm not sure how it is called, maybe bidirectional list or two-directional. How to use it and what it is. So for every x, at the end, it's very easy to know the next and the previous x. So actually we can implement this two-directional list by using two arrays, each let's say of size n, Okay. You can go from smallest to biggest and use union find with sizes. I'm not sure if it's obvious. Union find by default has some extra log in complexity, maybe log star, maybe some small log, but it's possible to do this like union find thing without log, implementing bidirectional list. This is like some special case. Okay, so first we can initialize our list by saying that for every index, next x is just this index plus 1, and previous one is index minus 1. And now, starting from the smallest number, so we want to unremove the x. We know from these values, we know where is the next x and previous one. So here, previous one would be that fake x at the beginning or at the end. So we have some index I. Let's take a look at this moment because it's more interesting. We want to now unremove this x. Well, remove this x and remove this number. For this x, if we know with array next and previous where is the previous and the next x, then we know. So here we knew that next of 4 was 2. So previous of 4 was 2. Next of 4 was 6. So this is fake x at the end. So this is n plus 1. What we should do to remove this 4 is to do next of previous of 4 is next of 4. So this way, for this previous x, for him we said what is the next x now. So we kind of put an arrow from here to here, and we do the same for the next guy to know his previous. Okay. Of course, this 4 here should be some I denoting what index now we consider. And now this has complexity, linear complexity. Let's show that. Let's see that on a drawing. So maybe here. So if we start from some sequence of numbers, very beautiful drawing, and for every number we know where is the next one and where is the previous one. And now when we want to remove something, for example, let's say we want to remove this, what we do? We want to remove this, we want to update the next and previous value for his neighbors. So we just change this to this. So this is what is done with this line. So this term, previous of I, means this guy. This is previous of I. And next of this guy we set to be next of I. So this is next of I. So this line changed this previous arrow to this one at the top. And similarly here we change the value previous. And this way, in constant time, we can remove elements. And then all the time we know for every x where is the next and the previous x. And do you have any questions about it? Okay, so if you have questions, do ask. And also I will say a few words about like more combinatorics approach, because here we just talked about probability. We said that we can count the number of good permutations and divide it by n factorial. Here we computed the probability that a permutation will be good. Odłączysz coś od prądu, bo here we computed probability that a random permutation would be good. So multiplying it by n factorial would give us the number of good permutations. But also we can just approach it from a side of counting permutations. And then instead of multiplying answer like this, what we do is here, for example, when we remove a 5, we change it into x. We know that we don't distinguish between one element on the left and 3 elements to the right. So what means multiplying the answer by the binomial coefficient like this. So generally it's if L and R means the number of elements to the left and right from this one, it's something like this. So binomial coefficient represents the number of ways to split a set of numbers into two sets with some sizes. What we do here at this moment is that we know that this value is the biggest one, so we know its value. And the remaining numbers 1, 2, 3, 4, we should split into two sets. One of size 1 and one of size 3. For example, we can decide that the left set will have value. For example, we can say that for L it will be set with only value 3, and right set will have 1, 2, 4. This is one of possibilities. And then of course here there would have to be 3, and here it would be 1, 2, 4 in some order. We don't know what order, and we don't care about it right now because it will be resolved in the future. Because then kind of of course we don't have recursion in our code here. We could, but it's when we iterate over every next smaller and smaller number, we kind of consider smaller and smaller intervals. So if we right now multiply the answer by this, we decide what numbers go to the left and what numbers could go to the right, and later we will consider those smaller intervals and we will multiply answer by something else, what will represent like counting the number of ways in this sub-interval. So these more combinatorics, like without probability approach, will just count the number of permutations, and of course if we want to find probability, then we divide the number of permutations by n factorial. Okay, and it's the end of this problem. Please ask questions if you have any, and that will be the end of my stream today. Once again, if you have suggestions, if you want to see some particular format or problems, the best either suggest now as a comment or say your opinion in code forces under my thread. And right now I think that at least one of my next streams will be writing a bot for a game, so kind of AI. Just usually AI means a bunch of ifs, but I think it will be fun, and also it will be nice to watch because something happens on a grid. I guess that next stream will be on Wednesday, but I'm not sure yet, and I will announce that. And that's it. Thank you very much for watching, and see you next time.